Okay. Welcome. I would like to welcome each and every one of you to the second webinar organized by Kerala State Council for Science, Technology and Environment. So today we are having the webinar on the prize which was awarded Nobel Prize in chemistry in the year 2021. So basically, as we are going to hear more about the essence of the work which was being awarded. So basically, as given in the website of the Royal Swedish Academy, so the work was on the development of a precise new tool for molecular construction, which is the Organo Catalysis, so which is believed to have is going to have a great impact on the pharmaceutical research and to make chemistry more greener, actually. So today we have one of the good speakers in the area of organocatalysis. Actually, we are lucky to have Dr. Ravi here today, who is currently the principal scientist at CSIR, National Institute for Interdisciplinary Science and Technology, which is a CSIR lab at Trivandrum. If you're going through his career, actually he did his BSc and MSc from Andhra University, and later MPhil at the Graduate Center, City University of New York in the year 2005, after which he continued there for his PhD in 2009. And he has been awarded many prestigious fellowships, including awards instituted by the Kerala State Council for Science, Technology and Environment, the KSCSTE Young Scientist Award in the year 2013. Then the Science Fellowship from the City University of New York, the Dr. Kafar Rose Dissertation Award from the university, and CERC Fast Track Fellowship for Young Scientists. He has over 46 publications and 2 patents. He has great professional experience. And as I already mentioned, he is the good speaker in the area of organocatalysis, as his research interests are in the development of novel synthetic methods of pharmaceutically relevant molecules, as well as new chemical entities, and synthetic carbohydrate chemistry. So on behalf of Kerala State Council for Science, Technology and Environment, and all the participants who joined us today for the webinar, I would like to welcome Dr. Ravi for the webinar. Over to you, sir.
Thank you, Arjun. I hope you can hear me.
Yes.
I would like to thank first the KSCSTE for giving me this opportunity to talk about the organocatalysis, which was chosen as the topic, the area for which the Nobel Prize was awarded in the year 2021 for chemistry. So this year, Nobel Prize in Chemistry was awarded to Benjamin List and David W.C. Macmillan for their pioneering work in the area of organocatalysis. So as this is a very general presentation, it's not a technical presentation. I would like to touch upon some of the basics of the area of organocatalysis. And prior to that, I would like to mention.
Hello, sir. You are not audible now. You are on mute.
Can you hear me?
No, it's okay.
Yeah. So what is a catalyst? Basically, catalyst is something which reduces the activation energy of a reaction from reactants to products. If the catalyst is not there, the activation energy is higher. And if the catalyst is there, the energy of activation is reduced so that it can be an efficient reaction. Now, this simple truth is helping the mankind, especially for carrying out many reactions in industries, whether it is pharmaceuticals or materials. Catalyst has a role everywhere. It is not just the catalyst in the area of pharmaceuticals, but it is also important to understand that there is something called as a biocatalyst. And we are all aware of a biocatalyst, which we call it as an enzyme. Enzyme basically drives many chemical reactions forward, and enzymes are nothing but organic molecules. So it is basically these enzymes, which are organic molecules, that drive the, or I should say, inspired these Nobel Prize winners to come up with a completely new area of, or a tool for conducting reactions, which is called as organocatalysis. So before we go into that, organocatalysis, I will be explaining some concepts on chirality. It's very important to understand what is meant by chirality. I'm trying to move my slide. Just please bear with me. Okay, can you hear me, right?
Yes, you can. Yes, we can.
Okay. So the Nobel Prize is widely regarded as the most prestigious award in the field of science, which is considered to be the greatest benefit it is given to the mankind through the scientific advances of the Nobel laureates. The Nobel Prize has bestowed to a number of categories by Swedish and Norwegian committees in recognition of cultural and scientific advances. So as I mentioned that before I go into the concept of organocatalysis, it's very important to understand what is meant by chirality, because that has a great influence in understanding the concept of organocatalysis. So as it is a general presentation, I'll be giving a very basic definition of what is chirality from the basics to the definition and its application. So let us take a look at chirality. Now, the word chirality is actually having the origin from Greek, which means handedness. So handedness, that is with respect to how different is the image in the mirror from the original image. So such handedness is also called as chiral. And if there are also molecules which are called as achiral. I'll come to that with an example. Any geometrical figure as chirality, if it is having a image which is a mirror image, and it cannot be brought to coincide with itself. So that is the concept of non-superimposability. So I'll explain that with the help of a hand. See, if you look at your left hand and right hand, both of them are mirror images. But if you try to superimpose these two mirror images, they don't superimpose. Okay. So the non-superimposability of the mirror images of your hands make your hand chiral. Okay. So if you look at a chemical point of view, the definition of chirality, it is more relevant towards carbon chemistry. In other words, carbon chemistry is nothing but organic chemistry. And if you look at a carbon, and this is in particular for biologists I'm talking, carbon is having a valency of 4. And if that valency of 4 for carbon is all single bonds, and if all these 4 single bonds are different, even if you have, let's say, for example, in this case, you have hydrogen, chlorine, fluorine, and bromine as the atoms, which is satisfying the 4 valency of carbon. And if this carbon is having 4 different attachments, then its mirror image, just like your left hand and right hand, are non-superimposable. That means if you take the right side structure of the mirror image and place it on top of the left side structure, you will see that the chlorine will coincide with bromine and the bromine will coincide with chlorine. So such a molecule is said to be non-superimposable. So that means that a carbon which is having 4 different attachments is considered to be a chiral carbon because it meets the criteria of non-superimposability. It's also known as asymmetric carbon. So sometimes the word asymmetry creates confusion. It doesn't mean that it doesn't have symmetry. It does have symmetry. But when you make a mirror image of it, and if you try to superimpose, then they don't superimpose. So such a criteria which makes the carbon chiral is the topic of today's discussion. So what is the difference between these two molecules, okay, which are non-superimposable mirror images, just like our left hand and right hand? So they have the same atoms and same bonds, and they do also have the same physical properties like melting point, boiling point, freezing point, and they also give the same spectra. But there is one property in which they differ. So that is the property which is called as optical rotation. So what are these molecules basically called as? For example, if you look at this example, this is a alanine. Alanine is having a mirror image. S-alanine is having a mirror image of R-alanine. And these two molecules are called as enantiomers. So non-superimposable mirror images of chiral carbons are called as enantiomers. And when these two enantiomers are present in equal proportion, they are called as a racemic mixture. Okay, so first I'm basically covering all the basic definitions that you come across in chirality. So that you understand more deeply what is the essence of chirality in this Nobel Prize. Okay, so racemic mixture is basically equal proportion of both the enantiomers. And in this example, we can see alanine is having a mirror image, and these mirror images are non-superimposable. So these two are called as enantiomers. But if they are present in equal proportion, they are called as racemic mixture of enantiomers. Now, as I mentioned that these two molecules have the same properties when it comes to, let's say, melting point, boiling point, and even spectra. But there is one property which makes it different from each other, and that is called as optical rotation. Enantiomers differ in one physical property, and that is the interaction of the molecule or the enantiomer with the plane polarized light. So when a molecule is placed in the path of the plane polarized light, then the single enantiomer will rotate the light in one direction. So if that direction is right side, that means on the right hand side, then it is called as dextrorotatory, which is given a designation as D. And if that plane polarized light is rotated on the left side of your that means if you are facing that light, your eyepiece over here, you can see I'm moving my cursor. This is your eyepiece, and if you are seeing that the plane polarized light is rotating towards the right side, it is dextrorotatory enantiomer. And if the plane polarized light is rotating left side, then it is levorotatory enantiomer. Okay, so this property of the enantiomer, also called as optical activity, is characteristic of each enantiomer, and such a enantiomer which exhibits this optical activity property through optical rotation is unique for the enantiomer. So if one of the enantiomer is having an optical rotation with a degree of plus 42, then the other enantiomer will have minus 42. Okay, so that is the exact opposite of the sign. So one enantiomer is plus 42, the other enantiomer is minus 42, for an example. So such enantiomers, if they are present in equal proportion, then plus 42 minus 42 cancels each other, then the net optical rotation is 0. Okay, so there will be nothing deflecting as far as the plane polarized light is concerned when you have a mixture of enantiomers in the sample tube. So the sample tube contains pure enantiomer, then you will find out whether it's a right side rotating or left side rotating. If it is right side, it is dextrorotatory. If it is left side, it is levorotatory. And on the other hand, if the sample tube is containing an equal proportion of both the enantiomers, then you will see that there is no rotation of the plane polarized light. The net result is 0. So such a molecule, which is a racemic mixture of 50-50 mixture of enantiomers, is said to be optically is optically active, but it is equal in proportion. That's why you're not able to see any deflection in the plane polarized light. So why do we have to understand the importance of chirality? So let us take a look at some natural products just for the sake of beginning. Carbon is a molecule which is a natural product, and in caraway, if you look at caraway, there is a carbon which is present as S enantiomer. But in spearmint, the same carbon is present as an R enantiomer. So nature produces one particular enantiomer preferentially. There is a reason for that. Okay, so nature prefers one particular enantiomer, and it doesn't produce racemic mixture. It produces one enantiomer in particular. So in natural products, we can see that very commonly. And in spearmint, the carbon is produced as R enantiomer. In caraway, the carbon isomer is produced as S enantiomer. Moving on, more examples. before going into the more examples, why nature prefer one particular enantiomer over the other. So this concept brings us to a term called as homochirality. See, all life on Earth uses only one single enantiomer of amino acids. For example, majority of all the amino acids are L amino acids, and majority of all the naturally occurring sugars are D sugars. Okay, so why these biomolecules are produced preferentially as homochiral, that means as a single enantiomer. There is some theory behind that. That means why the origin, what is the origin of homochirality? That means why amino acids are preferring only L form, not the D form. Okay, for example, in alanine, this is the structure of alanine. Why nature is preferring L-alanine over D-alanine? The theory goes that there may be during the Big Bang that there is a selective destruction of one enantiomer via a circularly polarized UV radiation. And there may be many events that might be happening during the formation of this universe where one of the enantiomer got selectively destroyed, which gave rise to preferential formation of one enantiomer only, and that led to the formation of life. Okay, so the compounds that occur in nature are generally optically active because living organisms tends to produce only one single enantiomer. Okay, or other words, the asymmetry of these molecules arises from the inherent chirality of the enzymes that are responsible for their production. Okay, so before going into the details of what is an enzyme and what enzyme is made up of, let us look at a few more examples of what is the significance of chirality. Okay, in pharmaceuticals also we come across many molecules which are chiral in nature, and there are many chiral molecules which are racemic also. For example, thalidomide. So when thalidomide was given to pregnant women in the early decades in the 20th century, the thalidomide which was produced as a racemic mixture of two enantiomers is prescribed to pregnant women, in particular for treatment of their morning sickness. Okay, but what happened was there was a severe tragedy as an aftermath, that the children that were born with some serious defects by having an amputated limbs or having all kind of congenital disorders. So the reason for that was found to be that one of the enantiomer is having indeed an effect on curing morning sickness for the pregnant woman and acting as a sedative. But the other enantiomer, that is S-thalidomide, was shown to be responsible for more than 2,000 cases of birth defects in children born to women who took the drug during their pregnancy. Okay, so this completely changed the scenario of the way the pharmaceutical drugs are made, especially when they are chiral drugs. One of the chiral drug is in particular given emphasis, or the chiral enantiomer, the enantiomer which is responsible for the therapeutic action is supposed to be given emphasis than producing racemic mixture of equal proportion of both the enantiomers. Okay, so we can see that more in examples. Soon after that, there are many other examples that have come to the light, where R-penicillamine is a molecule which can cause blindness, but the S-penicillamine can be an antidote for lead, gold, and mercury. Similarly, S-ibuprofen is active as a painkiller, and R-ibuprofen is inactive. Now, let me explain this particular concept of being inactive and active. So if you look at ibuprofen is not actually produced as S-ibuprofen in particular, because the R-ibuprofen is inactive. That means it doesn't have any effect. So it is easy to produce the racemic mixture of ibuprofen. That means a 50-50 mixture of both S-ibuprofen and R-ibuprofen. Because the R-ibuprofen is inactive, is proven to be inactive. So it doesn't matter even if we have a racemic mixture as a drug. Now, why it is important is because that is where the Nobel Prize has been given for this year in 2021. Or in other words, the racemic mixture is easy to produce. Okay, for carrying out any chemical reaction, it is easy to produce a racemic mixture, but it is very hard to produce a chirally pure enantiomer. That means either S enantiomer preferentially or R enantiomer preferentially. That is where the challenge is. So that is where the catalysis plays a major role, and organocatalysis in particular has a very significant role in producing one particular enantiomer preferentially over the other rather than producing a racemic mixture. Okay, so in ibuprofen it is okay because the other isomer is inactive, but for thalidomide it is not okay because the S-thalidomide is dangerous and R enantiomer of thalidomide is having a sedative action. So why does it happen that one particular enantiomer has a detrimental effect and one particular enantiomer has a desired effect? Okay, so it happens so that our receptors in the cellular membranes, whether it's a G protein coupled receptor or any other receptor on our cellular membrane, once it recognizes a foreign drug molecule, and when it reacts, when it binds to that receptor, there is a particular mechanism of lock and key. So it's like you place the correct key in the lock, then the lock will open, right? So if you have that lock and key model concept understanding, then it's easy to understand that if this square, triangle, or the cylinder is the receptor, then this amine or the carbonate or the carboxylate or the hydrogen of this particular drug molecule fits well with this receptor. So there is a perfect lock and key, there is a good interaction, and then the therapeutic action is going to happen. But if the other enantiomer is there, and that particular other enantiomer to this static receptor and to this mobile to this enantiomer, the square is not going to bind to the cylinder, the circular hydrogen is not going to bind to the square receptor, and the triangle may fit into the triangle, but the others don't. Therefore, there is no interaction here, and either it can be inactive, that means this particular enantiomer may not be having any therapeutic effect, or at the same time it can have a detrimental effect like the one which we have seen in thalidomide tragedy. Okay, so the first compound, which is on the left side, can bind to the receptor, while the right side compound cannot bind to the receptor. So this is the reason enantiomers have great significance, because they produce a very particular and pertinent biological response. So moving on to the Nobel Prize for this year 2021, after looking into the basics of chirality, enantiomers, racemic, optical rotation, etc. So organocatalysis is important to produce that particular enantiomer which is of desired nature. Whether it is R enantiomer or S enantiomer, by carefully tuning the catalyst which is responsible for producing one enantiomer in preference over the other, then we can produce enantiomers preferentially, which is required for pharmaceutical industries. Okay, so it turns out that organocatalysts are not new. Actually, organocatalysts are also present in our life from the beginning itself. See, our enzymes are nothing but organocatalysts, because enzymes are made up of organic molecules, right? So enzymes are nothing but polymers of amino acids, right? So these amino acids like proline, or you take serine, threonine, alanine, leucine, isoleucine, all these amino acids, whether you have neutral amino acids or acidic amino acids, basic amino acids, these all amino acids constitute one big protein structure which is responsible for enzymatic action as far as a biomolecule or biomolecular catalysis is concerned. But when it comes to organic chemistry, the reaction chemistry that you do in the lab artificially, different from your natural system, then can you mimic nature? That means, can you mimic an enzyme to produce the same effect of what an enzyme does, of what a biocatalyst does? Can you do the same thing in the lab artificially? Then you are producing something called as organocatalysis. So there are three different kinds of catalysis. We already know about enzymes, so that is biocatalysis. But when it comes to organic chemistry of using catalysts, there are two kinds of catalysts. Either there are a metal catalysts like transition metal catalysts in particular, or organocatalysts. So it is the organocatalyst for which the Nobel Prize has been given. And these organocatalysts are nothing but small molecules, unlike enzymes, which are macromolecules. And these organocatalysts serve as the same role as that of the enzymes or biomolecules in construction of molecules. So if enzymes are life's catalysts, the organic reactions through which these organocatalysts are conducted, they can be catalysts which will be essentially driving chemical reactions. So enzymes operate with very good precision to produce selectively one enantiomer. So enzymes are built from hundreds of amino acids, as I mentioned. And what happened was when Benjamin List, who is one of the Nobel laureate for this year, Chemistry Prize 2021, when he was actually working originally with antibodies. Okay, so he was working with antibodies. Antibodies are nothing but giant macromolecules which are made up of amino acids. So when he was working on antibodies, he was essentially working with antibodies that have a particular functionality of serving as a catalyst for a particular reaction. What occurred to his mind was, which was out of the box question, that when such an antibody, which is made up of a bunch of amino acids, is serving the purpose of catalysis, why not a one particular amino acid where the actual reaction is taking place? So that's what occurred in his mind, that a particular amino acid is only responsible for carrying out the chemical reaction. Then why is it necessary for all that amino acids in the bunch of that antibody to serve as a catalyst? So this question raised in his mind that can all the amino acids necessary, or is it just one amino acid that is required for the catalysis to take place? So that particular single amino acid can be a simple molecule which can do the job of catalysis. So that's what he applied in his reaction, and he turned out to be successful for his reaction, which is called as the famous Aldol reaction. And the amino acid which was responsible for carrying out that Aldol reaction, which he used, was called as proline amino acid. So proline is having is the only cyclic amino acid that is present in nature, which is having a 5-membered ring with the nitrogen and the carboxylic acid group. Moving on to the other Nobel laureate, David Macmillan. He originally used metal catalyst during his postdoc and during his research, and he found out that metal catalysts are indeed expensive to use, and they are very difficult to handle, because metal catalysts require some very stringent conditions to do organic chemistry, like moisture-free conditions or oxygen-free conditions. So they have great amount of demands. As a result, it is very expensive to use metal catalysts and very sensitive to use metal catalysts. So it will be very difficult if you use metal catalysts in industry, because it will complicate the large-scale industrial manufacturing. Therefore, he came up with this idea that can we use an organocatalyst on the other hand, which can serve the category, which can serve the idea of using the metal catalyst as an alternative. Okay, so this idea led David Macmillan to design some organic molecules which can behave similar to metals. So he used that simple design, which I will show in detail with respect to the structure later. But this is the Macmillan's catalyst, which is called as imidazolidinone, which serves as a catalyst for his organic reaction, for which he conducted, is called as a Diels-Alder reaction, which is also a famous organic reaction in regular practice of organic chemistry. See, these organic catalysts are not just important for doing reactions. They have a great application, and the most important application is in pharmaceuticals. Okay, so organocatalysts had a very significant impact in pharmaceutical research for synthesis of chiral drugs, because we need to produce one particular enantiomer. And examples of such include paroxetine, which is used in treatment of anxiety and depression, antiviral medication, which is also called as Tamiflu or oseltamivir, which is used in the treatment of respiratory infections. And such organocatalysts serves as the third pillar of catalysis, complementing biocatalysis and transition metal catalysis. So this is a reaction which I'm showing to you in brief, where this particular proline based mimic also is given here. This structure serves as the organocatalyst in conducting an organochemical reaction to produce one particular enantiomer preferentially, which serves as an intermediate and taken in next few steps to convert into the antiviral drug called as oseltamivir. Okay. So List and Macmillan, they have put forth their general concept of using chiral molecules such as proline and imidazolidinone, and they applied a particular concept of organic chemistry using these organocatalysts for their reactions of Aldol reaction and Diels-Alder reaction respectively, where in Aldol reaction, a particular intermediate which is formed is called as enamine. So in other words, using a proline, the Aldol reaction was conducted by formation of an intermediate called as enamine, which is also called as enamine catalysis using proline. On the other hand, when it comes to Macmillan, it forms a particular intermediate called as iminium ion. So that means the Macmillan's imidazolidinone catalyst will first react with the aldehyde, and then it forms iminium ion, and then it produces the endoisomer and exoisomers, where the one of the isomer, endoisomer, is the preferred one compared to the exoisomer. So when it comes to Benjamin List, he used proline, and with the help of proline through enamine catalysis, he produced Aldol product. When it comes to David Macmillan, he used imidazolidinone, which served as a catalyst for Diels-Alder reaction to produce the cyclic bicyclic products. And it did not stop there. Both List and Macmillan have continued their activities in the field, and they applied this organocatalysis of using proline and imidazolidinone as catalyst in several named organic reactions, in several reactions. Benjamin List in particular, he used L-proline as a catalyst for the development of efficient Aldol reactions, manic reactions, double manic reactions, alpha amination of aldehydes, and conjugate reductions, among other processes. And when it comes to Macmillan, he used the imidazolidinone catalyst, which he has developed in several dipolar cycloaddition reactions, Friedel-Crafts reaction, Michael addition reactions, and domino reactions, including other transformations. So this is what is very important to understand. At this point, I would like to stop. And I would like to mention here that organocatalysis is not something which was brought forward by Benjamin List or Macmillan. Okay, organocatalysis happened to be there in the past also. Several reactions were reported, but they were all isolated reactions. That means they were all reactions were conducted for one time, but not applied greatly in depth or not studied in depth. Okay, so this is very important for us to understand today, that Nobel laureates are given Nobel Prize not for one particular invention or not for one particular discovery. If they find that their invention is having some application, you need to continue in that activity or in that field and establish that field to a greater extent so that it has a wider application and it has great advantage to the humanity. In this case, we are talking about pharmaceuticals, developing affordable pharmaceuticals as something which is beneficial to the humanity. So that is the reason why List and Macmillan got Nobel Prize. It is not that they have invented organocatalysis or they have introduced Macmillan. They have introduced organocatalysis to the field of organic chemistry. There was catalysis in the past also. Organocatalysts were used in the past also. But these two people, they have pioneered in this area of organocatalysis by expanding the field and by including several reactions and activities in this particular field of organic chemistry, which was eventually useful for pharmaceutical industries. So when it goes to the applications of organocatalysis in synthesis of complex organic molecules, cascade reactions that mimic enzymatic synthesis, facilitated synthesis of alpha tocopherol, vitamin E, and organocatalytic approach was also useful for synthesis of antihypertensive drug called as aliskiren, the structure of these two molecules are given over here. So with this, I would like to conclude my presentation, where one of the member of Nobel Committee for Chemistry, Peter Somfoy, mentioned that the organocatalysis area is so vast that it not only comprises enamine and iminium ion catalysis. And today, organocatalysis has matured into a tool that it is routinely used in synthesis planning and execution, both in industry and academia. So I hope you all were convinced, and I'll be more than happy to take many questions from the audience today on the area of organocatalysis, and in particular, the Nobel Prize, which was awarded for this year of 2021. Thank you very much.
Thank you, sir. Thank you. Thank you very much for the really interesting talk. I think you could clearly give us an overall idea about the organocatalysis and why it was awarded the Nobel Prize. So now the platform is open for questions. So either you can, the participants can post your questions in the comment box, or can unmute yourself and talk to him.
Arjun, if there are any questions which are typed, kindly read it out.
Sure, sir. So I think maybe some of them might be typing. So in between, I would like to ask, basically before the organocatalysis, so what was a conventional method used in pharmaceutical industry for the production of this compounds? Like, was it exclusively on biocatalysis or metal based catalysis?
There are actually metal based also. Basically, if you look at Aldol reaction, I will go back to the Aldol reaction. It's very simple to understand. So Aldol reaction is there from time immemorial. Even nature uses Aldol reaction to produce beta hydroxy carbonyl systems. But when it comes to industry, when they do this Aldol reaction, if it was not for proline, then you will not get this preferential selection of producing only one enantiomer over the other.
Okay. Mm-hmm.
That means if you use D-proline, for example, in place of L-proline, if we use D-proline, we will be getting the hydroxy on the other side.
Okay. Mm-hmm.
So if you take a look at this organocatalyst and the chirality which is embedded in the system, you see that organocatalysis are all chiral molecules. Only catalysts are nothing but chiral. It is the chiral nature of that particular organocatalyst which prefers one particular enantiomer production. But
okay.
If you ask me if industry uses L-proline, it depends. It varies from case to case basis. If they are interested in producing racemic mixture, then even base, a simple base which produces an enolate will react with the aldehyde and produces that. And if it was an acid, it produces, it gives rise to an enol intermediate which reacts with the aldehyde and produces this product.
Okay. So I think even based on the cost level, I think this has much more, is better compared to other enzymes or other mode of catalysis, isn't it, sir?
Absolutely. L-proline is nothing but a natural amino acid. Okay. L-proline is available in plenty. Whereas if you look at this imidazolidinone, imidazolidinone is actually also listed in the Aldrich catalog. It takes few steps to prepare this molecule. It is not something which is produced by nature. That is what makes this molecule unique, because it is a designed molecule, designed with an intention of producing one particular enantiomer. So this molecule, imidazolidinone, is produced by some synthesis, whereas L-proline is a natural product, natural amino acid. I think there is some question. I think something popped up. Can you please read out?
Sure. The question is by Dr. M. Narain Manuel. He says, I believe there must have been efforts to study the mechanism of how these organic molecules catalyze the reaction. Can you please shed some light on it?
Yeah, sure. If I'm on the right slide actually to explain the mechanism of this particular Aldol reaction. See, what happens is when you take this acetone, right? acetone reacts in presence of carboxylic acid and secondary amine, the acid can protonate the carbonyl, and then the protonated carbonyl is activated. So once the protonated carbonyl is activated, oxygen is protonated, then the secondary amine will react with that and it will form imine first. Imine means NC double bond. Then imine is unstable because the nitrogen is having 4 bonds. It tends to go back to its trivalent state. So it will be stabilized by proton, with the loss of the proton to stabilize that positive charge, and thus it produces enamine. Enamines are actually alpha beta unsaturated amines. Okay, so enamines are alpha beta unsaturated amines are actually nucleophilic in nature, and we have an electrophile. So the nucleophilic enamine will react with the electrophilic aldehyde and produces this beta hydroxy carbonyl system. But originally it will be imine, and then it will be hydrolyzed to regenerate the proline catalyst. Whereas in the imidazolidinone catalyst, basically again the same mechanism. The secondary amine, this nitrogen is quite stable because it's an amide bond. The secondary amine will first form imine, and that imine basically activates this particular double bond for it to react. So this will become, in Diels-Alder reaction, there is something called as a diene and a dienophile. So this will take the role of a dienophile, and this is the diene. So the diene and dienophile will react to form the Diels-Alder products. Any other questions, Arjun? Did I clarify? Doctor, can you just give a message to Arun if it is okay, or if you need more explanation?
Yeah, Dr. Manuel, was this? So he's asking. So this is basically like intermolecular reaction.
This is intermolecular, not intra. It's not intra, it's inter, because 2 molecules are there. So it is intermolecular reaction. Yeah.
So another question is on the importance of proline. Why proline is having so much importance?
So the thing is organo question arises. There are actually, everybody should understand that there is also criticism for this year's Nobel Prize in 2021 being given to organo catalysis. People should understand that people who are criticizing are people who are telling that they have a particular, for example, proline in this case. You see, proline is having secondary amine and it is having a ketone. So the secondary amine or the ketone or the aldehyde should go through, that means you must have a carbonyl for this proline to react. Let's say if you just have a CH2 over here, this will not react. It's not selective. Sorry, it is selective. That means it is the catalyst which is developed by, which is used by NIIST, or the catalyst which is used by Macmillan, are having a very selective or a particular way of reacting. That means they have a particular substrate, then only they will react. That means they are very good for Aldol reaction, they are very good for Mannich reaction, they are very good for cascade reaction. And in particular, wherever there is a carbonyl system, then only this catalyst will start reacting. So that is where the criticism started, that this is so selective, it is not generalized. That means organocatalyst is not generalized. They are very selective, but they are selective for one particular reaction. And but what happens is that those reactions are very famous and quite often used in pharmaceutical industry. Therefore, this organocatalyst can be a greener substitute for toxic metal catalyst in industry. That is why the Nobel Prize was given. Maybe I digressed from the point, but the point what I'd like to make here is that they are selective. Organocatalysts, in this case in particular, L-proline or imidazolidinone, they are selective. If carbonyl is not there, this catalysis will not take place. That is why NIIST catalyst is going through enamine, and the Nobel Prize was given for enamine. They call it in the first slide itself. I have shown. I think I have shown. One second. Yeah, here, if you look at this title, you see the title. The title is saying that List and Macmillan put forth a general concept of using chiral amines in asymmetric enamine-iminium catalysis. What is enamine? Enamine is nothing but it requires an aldehyde or a carbonyl system. Iminium also requires a carbonyl system. So they are very selective. They can't be generalized for other systems. So the selective nature of these substrates makes them useful. That means these organocatalysts useful for only one particular kind of reactions. In this case, Aldol reaction and Diels-Alder reaction. Yeah.
Yeah. Okay. So their specific nature, specific characteristic is giving them importance to act as a catalyst.
Yeah, they need carbonyl substrates.
Okay. Okay. Do we have any other question?
I think I read one question.
Yeah. Asking actually, Diels-Alder require any catalyst?
Yeah, actually, Diels-Alder reaction has a selectivity issue of endo versus exo. As you can see in the bottom here, endo versus exo. If you use this particular catalyst, the endo isomer is produced preferentially. That is why the catalyst is definitely essential for the endo selectivity of the Diels-Alder reaction. Catalyst is required. If catalyst is not there, the selectivity won't be there. Yeah.
Another question is, by which characterization method we will be able to identify organocatalysts easier?
Organocatalyst is an application. The characterization comes to the product that we form. In this example, Aldol product, or in this form, in this example, the bicyclic product, the bridged bicyclic structure. In the characterization comes for organic chemistry. The best tool for organic chemistry as far as characterization is concerned is NMR only. So for being a good organic chemist, one should have the ability to characterize compounds from the NMR spectrum. NMR is a very essential tool for organic chemistry.
So do you see application of this organocatalysis in any other areas, like apart from the pharmaceutical industry?
Basically, their application so far is being limited to organic reactions. But these organic products can have an application. For example, let us take a look at this bottom example, endo product. Okay. Now this endo product is having a double bond. Okay. Now this double bond actually can give a new idea. What is that idea? The idea is, let us apply another Nobel Prize which was given in the past. And that Nobel Prize was given to a guy by name Grubbs. And what is his invention? Grubbs' invention was cross metathesis. Cross metathesis, there again, it is in particular for double bonds. So cross metathesis can be applied. Grubbs catalyst, again, that is catalyst, which is ruthenium based. It is a metal based catalyst, for which Grubbs and Schröck got Nobel Prizes. And Grubbs used ruthenium, and his ruthenium metal catalyst, right, has been applied for the concept of metathesis. Now, there is a concept which is used quite extensively, and that was called as ring opening polymerization. Ring opening metathesis polymerization, ROMP, ring opening metathesis polymerization. And for that ring opening metathesis polymerization, the best example will be this bicyclic structure only, where the double bond opens up with the help of ruthenium, with the help of his ruthenium Grubbs catalyst, and then it can polymerize. Okay, so once it polymerizes, that polymer can be a material interest. It may not be of pharmaceutical interest anymore. It can be of material interest. So as far as organocatalyst is concerned, they have an application in forming, let's say, a Diels-Alder product or an aldol product, or a manic product, or a cascade reaction product, or a dipolar cycloaddition product. But that product can have another application. So that means that product need not be pharmaceutical. That product can be a substrate for another reaction. In this example, I mentioned a Grubbs catalyst, where it can participate in ROMP, which can give rise to another product, which is a polymer, and that polymer can have material application. Okay, so it depends on how you look at it.
Okay, the kind of the product which you're looking for.
Yeah, that product can have application in materials as well.
Yeah, very true. Okay, we have another question, sir. Like, so can we say these organocatalysts are disymmetric species?
They are asymmetric carbons. It is used interchangeably, but it is confusing. It is better to call as chiral molecules. They are chiral molecules, so they have a chiral center. So yes, organocatalysts have chiral centers. Answer is yes. They are asymmetric in nature, or disymmetric, as if you want to call it, but it will create confusion to the students. In case if we are teachers and if we are teaching, it is better to use the word chirality more in a generalized form than asymmetry, dissymmetry, etc. So yes, chiral molecules is what I prefer to call. They are having chiral centers. Organocatalysts have chiral centers.
Okay, sir. I think we don't have any other question. Okay, sir. On behalf of KSCSTE and all the participants, I would like to extend sincere gratitude to you, sir. It was really interesting to listen to you. You have actually explained it in a so basic manner that I think even those who are not in the field of chemistry could really get a glance of the work they have done, actually. Thank you very much, sir.
Thank you so much again for listening and having an interest towards attending this webinar. You made my day. Thank you very much. And I thank Arjun as well as KSCSTE. Thank you so much again.
Thank you, sir. And thank you all participants for joining us today. Tomorrow we have the third one on the Nobel Prize in the field of medicine at 7 p.m. exactly, and the same link can be used. Thank you, everyone. Thank you. Good night.
Good night.
Good night.